Hello, so this is video number 2 of section 7.2. So this is the penultimate video of the penultimate section of the penultimate day of lectures, and I'm recording this in the penultimate week of the course. We ended last video with sort of discussing, we defined quadratic forms, and then we talked about the terms xi times xj, where I was not equal to j, as being cross-product terms, right? And I kind of mentioned that for a variety of reasons, we like to look at quadratic forms that don't contain cross-product terms. And so today I want to kind of go over the method that we can use to transform quadratic forms that contain cross-product terms into quadratic forms that do not contain cross-product terms. And so the way we're going to do that is with what we call a change of variable. And this will closely mirror the ideas of like a change of basis from chapters 4 and 5 when we went over change of basis matrices. And if you remember that diagram where, depending on what basis we were looking at the linear transformation in, we could kind of say, well, this is like the same linear transformation, but studied under a different type of basis. And that's kind of what we're going to be doing here with the functions q of x. So we say that if x is a vector of variables in Rn, then a change of variable is an equation of the form x equals p times y, or it could equivalently be stated as p inverse of x is equal to y, because we say that P is an invertible matrix and Y is a new variable vector. And so I will convince you that defining it in this way will make everything work out the way we want it to in a second. But notice that in doing this, if you go back to chapter 4, I want to say it was section 4.4 or around there, Y is the coordinate vector of x under the basis of Rn defined by the columns of P. So basically what we're doing here is we're just performing a change of variable, or if you prefer, a change of basis, so that we can look at our quadratic form in a different way, right? So we want to perform a change of basis. And remember, what's going on here is basically what's going on with, or what's going on when we perform change of bases with functions is we're looking at the same function. We're just looking at the vectors under a different basis, right? And so our goal in doing this is to, in a sense, preserve this function, but rewrite it as y transpose times d times y, where d is a matrix such that this quadratic form has no cross-product term. Right, so what we're doing is we're saying we're going to relate x and y in this way, and if we do this, then we get this nice equality, where our original quadratic form is equal to this new quadratic form, again, where x and y are related like this, but this new quadratic form has no cross-product term. So I like to think of it kind of like this, that we're changing the basis, so we're changing the way we look at the function, but we're not actually changing the function. So why can we do this? And how can we do this? So doing this in this way is going to rely on the fact that A is a symmetric matrix, and that A, as a symmetric matrix, is orthogonally diagonalizable. So this is how to find P and D for a change of variable. So, like I just said, A is symmetric. And so A is orthogonally diagonalizable. Well, what does that mean? This means that A is equal to P times D times P inverse. But since P is an orthogonal matrix, remember, the inverse of P is just equal to the transpose of P. So this is actually equal to P times D times P transpose. And it turns out that the matrices P and D given by this orthogonal diagonalization are the exact matrices we want to use. So to verify that this is in fact the case, we will verify this, that in fact, if we let P be our change of variable matrix, so that is for each variable vector x, we're going to let x equal P times this new vector variable y. And remember, this is equivalent to stating that the new variable vector y we want to solve for is equal to P inverse times x, but remember P inverse is equal to P transpose. So the new variable vector we want, we're going to define by taking our old variable vector and multiplying it on the left by P transpose. So now, does this actually transform our old quadratic form, Q of x equals x transpose A x into a new quadratic form with this variable vector and diagonal matrix D? I think the answer is yes. So the first thing we want to do is replace our x's here with these p times y's. So this will be p y transpose times A times p times y. Evaluate the transpose, we get y transpose times p transpose AP times y. And sure enough, if I were to solve for D in this diagonalization equation, notice I would just multiply everything over here, and we do get, in fact, that D is equal to P transpose AP. And so, sure enough, letting the matrices P and D defined in this way perform our change of variable, we get what our original goal was. And remember, in the examples, right, the cross product terms came from those specific constants which were not on the diagonal of whatever matrix we were looking at. And so here, I've got a diagonal matrix whose, as we'll see later, this actually will be useful, whose diagonal entries are the eigenvalues of this original matrix A, and this matrix P, which is performing this change of variable. So again, we're looking at the same function, but just under a different basis, right? So remember, you can think of these vectors y and x as, in a sense, being the same, but just vectors represented under a different basis. So what can we do now? Well, we can start with quadratic forms that contain cross-product terms and transform them into quadratic forms that do not contain cross-product terms. And all it takes is orthogonally diagonalizing a matrix. So suppose that we've got the following quadratic form. Where A is equal to the matrix 4, -2, -2, 4. So we want to make a change of variable that transforms Q into a quadratic form with no cross product term. So to do this, remember the first thing we want to do is orthogonally diagonalize A. But to orthogonally diagonalize A, we need to find the eigenvalues and eigenvectors of A. So for the sake of time, I will just give you the eigenvalues and eigenvectors. So note that the eigenvalues and eigenvectors of A. And always with this, if you do want to see a full solution for finding these, let me know, and I can certainly send one to you. A should have two eigenvalues, lambda 1 and lambda 2, where lambda 1 is equal to 2, with corresponding eigenvector v1 being 1, 1. Yeah, and that follows because the row sums of A are all equal to 2. And then lambda 2 equals 6 with corresponding eigenvector 1, negative 1. So the good news is that v1 and v2, since A is symmetric, are automatically orthogonal. The bad news is that these are not normalized vectors, right? Remember, we want P to be an orthogonal matrix, which means the columns of P should be orthonormal vectors. So here U1 is going to be the normalized vector V1, and U2 is going to be the normalized vector V2. And so each of these vectors has norm root 2, so this will be the vector 1 over root 2, 1 over root 2. And so our change of variable matrix P is the following matrix. And so then the change of variable, we let x equal p times y, implying that x transpose a x is equal to y transpose d times y, where d is equal to the diagonal matrix, whose entries are the eigenvalues of A, so 2, 0, 0, 6. Again, so notice here, the first entry corresponds to its eigenvector, and the second entry corresponds to its eigenvector in order for P. And so notice then that y transpose d times y is equal to 2 y1 squared plus 6 y2 squared. And so if we perform this change of variable, where x is equal to p times y, then we get that these two quadratic forms, x transpose a times x and y transpose d times y, are equal. But notice this quadratic form, compared to the one defined by y, has no cross product term. So really, when you're asked to do this, you're just asked to orthogonally diagonalize A. provide the matrix P, which is actually diagonalizing A, and then potentially provide the new quadratic form, which is equal to the old one. So why do we do this? So first I want to state a theorem basically saying we can always do this, in particular because we define quadratic forms using symmetric matrices. And then I'll give a little bit of geometric interpretation or reasoning as to why we do this, which also kind of corresponds to the name of the theorem. So this is called the principal axes theorem. And this says that basically what we just did, we can always do. So let A be an n by n symmetric matrix. And there is an orthogonal change of variable. X equals P times Y. That transforms the quadratic form X transpose AX into a quadratic form Y transpose D times Y, where this quadratic form has no cross product term. So why is this called the principal axes theorem? So it turns out that if we look at the two-dimensional plane and look at the set of solutions to the following matrix equation, where here A is a 2 by 2 matrix and C is a scalar, it turns out that, and again, here X is a vector of variables x1, x2. It turns out that the set of solutions, x1, x2, given a matrix and given a scalar C, not always, but quite often, actually corresponds to an ellipse or a hyperbola in the plane. So for example, see if I can draw an ellipse here. It's a little not ellipse. It kind of looks like an avocado. Imagine that's an ellipse. It corresponds to an ellipse in the plane, right? So this is actually defined by the function x transpose AX is equal to C. Let's see if I can make this a little more ellipse-like. That's maybe a little more ellipse-like. So when we look at ellipses, ellipses have two axes, which we call the principal axes of the ellipse, right? It has this axis going this way and this axis going this way through the ellipse, right? And so these principal axes correspond to a quadratic form whose matrix has a cross product term, right? So if the ellipse has a set of principal axes that in fact are different from the set of actual xy axes, this ellipse probably has a cross product term. I'm not actually sure offhand if that's always the case, but I think it is. But what a change of variable does, so if we make a change of variable x equals p times y to eliminate cross product terms, what we do is we actually take the same ellipse and we just rotate it around the axis so that our ellipse has its principal axes located at the actual x and y axis. So basically what we're doing is we're changing the axes of our graph so that they rotate to be the actual x and y axis. And so in this way, you know how I said we're looking at the same function under a different basis? That's kind of what we're doing, geometrically when we make this. And so there's actually a picture of a hyperbola doing the same thing in your book. But when we make this sort of rotation, what we're doing is we're looking at the same ellipse, right? If you can imagine that I managed to successfully draw an identical ellipse, all we're doing is we're taking this ellipse and we're rotating it around so its principal axes are the x and y axis. And that's what we're doing when we eliminate the cross product term. Right? In the same way that we're looking at the same function under a different basis, we're looking at the same ellipse, just using different principal axes. And so you could do the same thing with a hyperbola, which I will maybe attempt to draw. That might actually be a little easier than an ellipse. And so depending on the symmetric matrix you choose, you could, again, use this type of equation to define a hyperbola or an ellipse. So a hyperbola with symmetric axes not as your x and y axis. Let me actually make sure I get this right. So a hyperbola without whose might look something like this, right? Where this is a hyperbola whose principal axes are not focused at the x and y axis. So if you can imagine here, like this hyperbola isn't, but again, much in the same way we can shift this hyperbola so now its major and minor axes are at the x and y axis. So you can imagine the hyperbola shifting this way, and it's kind of the same idea. So we've got one more video left of this section, video 3, coming up next.